Okay, good morning. How are you guys? Hopefully no dryers starting fires. Okay, so last time we left off here, started talking about coagulation, and just now I was double checking kind of where we are with the tentative schedule in our syllabus. And I realized we spent a little extra time somewhere because maybe we ought to be talking about granular filtration today. It's a relatively simple topic, so I think, depending on how today goes, maybe we'll load up those slides and get going on them. But I don't think we need 2 lectures to cover that. So that'll probably just be next time. And I'll probably save the discussion on homework 1 until the exam review day, and then I'll be assigning another kind of smaller homework on filtration, granular membrane filtration. And we'll go over both of those homeworks on the 27th. So that's the current plan. There's some confusion. And the slides that I posted I think I did post this set. Some of them are overlapping a little bit, so it's perhaps some confusion, but I do apologize. But you should have the slides there, and should have this. So we left off on this page. I'm not sure if this is exactly the notes from last time for us, or if this was the previous year. But essentially, what we were talking about is if we have some surface, and we're going to use that surface as a contrast to the solution in terms of how much are we mixing. We want to know how much we're mixing to get some idea of how fast are we going to be flocculating our particles. So if we have a couple particles here, let's say 2, and they're going to merge into 1, how quickly is that reaction going to happen? So we're exploring how to find the K here is really our goal. And one of the important parameters is going to be how intense is our mixing. So we're going to sort of make an assumption that we're not mixing too intensely. So we're not in like a turbulent mode. Then if we're not in turbulent mode, then we essentially, that assumption is going to mean that we're not going to break apart the particles. Or the aggregates that we're forming. Okay, so assuming we're not breaking apart the aggregates, then the more intense we are mixing, the better, in a sense of the particles are going to contact each other more often. And so then the way we're describing this G, this is our mixing intensity, that's our parameter we'll use to kind of inform that the rate constant in terms of how often they're going to meet. That's going to depend on the gradient with which the speed of the water, this velocity term here, V, going to the right, you could be thinking about like a paddle going through the water, and there's going to be some speed of the water being pushed to the side, or perhaps the water is just flowing next to the reactor basin, and this surface here is the reactor basin wall, and the forces of drag are going to slow that water down as it approaches the wall itself. So you'll have small velocity terms here, and they're going to grow. The difference between the surface and the speed of the water is going to be greater a little further away because the drag is not so intense over there. So that gradient then, the change in velocity over change in distance, is going to be our mixing intensity. And if you think about it, the units are going to work out because dV, that would be change in velocity, is meters per second. And then dy, how far away from the surface are you, that's meters here. And so that's going to leave us with per second. should be pretty familiar in terms of like our typical rate constants, first order are per second. So that's kind of lining us up well here. So we know that whatever expression for G, this mixing intensity, if that's how we're defining it, has to be in per time units. So it turns out that a good equation, I'm not deriving this, but a good equation for the mixing intensity is going to be the square root of the power that's being input. So if we have like a propeller, we apply some power to that propeller and it's mixing. That power divided by the dynamic viscosity of the water and then the volume of the basin. So we've been dealing with a few different volumes, a few different V's. So this uppercase V subscript B, it's going to be the volume of the basin of that chamber. And that's going to be, so that's kind of the power over some amount of water that has such and such a viscosity. So you can imagine you're going to get a lot less mixing if you are trying to mix a batch of molasses. You're going to need a lot of power to get the same amount of mixing, right? That's essentially what this is saying. Okay, so power then is in watts. That's going to give us the per second term there. Bless you. Then we have dynamic viscosity of water. It's kilograms per meter per second, and this cubic meters here. So those units, if we were to work them out, are going to yield per second as well. So it matches up, and that gives us a definition that we can relate to the water and basin conditions. So we are applying some sort of power. We have such and such a large reactor, and we have the temperature of the water. Right? So those are the kind of design parameters that we can work with. Then we know something about the mixing intensity. Okay, so that's one component of our K for rate of aggregation, we can say, is what we're looking for. So G is going to go into K, as we'll see in a second. So this, we're just sort of building, okay, how do we know how quickly these particles are going to meet? Okay, so before we get to the K itself, let's remind ourselves what exactly this K is doing for us. So I mentioned this last time, but I'd like to just take a slide and flesh it out a little bit more clearly here. So we have some reaction. This is, we're going to describe it in this manner. dN dt, so that's the number of particles, the particle concentration by number. It's changing over time, so that's an accumulation term, or the change term. So dN dt, call it R of n maybe, equals negative k times n to the 1 power. Right, so we've got a first order decay reaction, which makes sense because as we decrease the number, we didn't cause any to disappear. They're all just sticking to each other. So there's fewer of them, but they are becoming larger particles. So let's say we have 5, 6, 7, 8, 9. Let's put 12 little particles here. And then during our flocculation, we ultimately end up with, let's say, 2 particles, each with 6 of the subunits. Something like that. So here, in this case, we went from n equals 12. We could call it particles per volume. Let's just imagine this is per liter here, as if that's a liter of water. And then we'll call this n initial. So n initial, and then the n final would be 2. Okay, and again, we have some number per volume as the units. In this case, since we already said particles per liter, we can just say per liter. Okay, does that make sense? We still have the same volume, we're going to assume, of particles. We're going to have the same mass and all of that. We've just decreased the number of them by sticking them together. So that means this first order decay is a correct way to describe that. They need to meet each other, so it depends on how many of them there are, and they are decaying in terms of the number is decreasing. And so this K is really what I was talking about when I was saying, okay, well, let's find what that K depends on. That's where the mixing intensity is going to come in, as well as some other parameters. Okay, so this then can give us a way to describe flocculation in a larger chamber, right? Because this is our rate equation, we can put that into a mass balance. So then we can take R of n and put it into mass balances to design flocculation. Processes. Okay, one thing to consider here before I move on is there's actually one, I guess a technical term, sort of, a way we can talk about these particles and this dynamic of a new particle formed based on some number of old particles. And that is, if we take a look at how we're describing n and n naught, we can say that the initial amount per final particle, so the initial amount of particles per volume divided by the final amount of particles per volume, is essentially going to give us the number of initial particles in each final particle. So this is going to be the number of initial particle in each, I'm going to call them aggregate. Aggregate particle. So we're going to still treat them both as particles, but I'm saying aggregate just to convey that it has a bunch of them stuck together now. And this works, even though this is concentrations, it's because it's the same denominator, right? So liters and liters. So that means in this case, we initially had 12 and now we have 2. That means for this case, n naught over n is equal to 6. So therefore, there are 6 initial per final particle. And what you'll notice here is that makes more intuitive sense than looking at it in terms of n over n naught, right? Most of the time we look at, okay, well, what fraction has been removed? Because we care about, maybe what fraction of the bacteria died or something like that. What percentage are we dealing with? Here, if we're going to try to learn something about the new particles, it actually makes more sense to invert that and say, okay, well, how many of the initial ones are in each of these final ones? So it's just a little bit algebra. It's just flipping it, right? In terms of how we want to look at the system to learn something about it or to manipulate. So just keep that in mind. Most of the time we do n over n naught. This case, usually we'll be doing n naught over n just because of the meaning that comes out of it. Okay, and we'll work on a practice problem today to highlight that. Okay, for the rate constant then. Been talking up this K for a while, so let's define it. K is going to be equal to this alpha times 4 times omega times that mixing intensity, all divided by pi. And it should be in per second units because G was in per second units. And we need a per time unit for a first order rate constant. Okay, so that begs the question, okay, what are these other pieces here? We know 4, we know G, and we know pi. That stuff we can handle. Well, this alpha here, this is going to be collision efficiency. And we're going to say, if two particles collide, what percentage of the time do they actually stick together? So this is essentially our coagulation or our coagulant, ANT, I think. coagulant. If it does a good job, then the collision efficiency should be perfect, right? So if we completely destabilized the particles, then this value should be 1, because every time they meet, they stick together and form a new particle. That's a larger particle from the two of them. So we'll say, I already kind of wrote it here. Yeah, so I already wrote it here. So we've got when this alpha is equal to 1, we have complete destabilization. And that means they're very sticky. So anytime they meet, they're going to stick together. On the opposite end of the spectrum, if this value is 0, then they never, 0% of the time they collide, they form a new particle. And that means that if we put a 0 here, the rate constant goes to 0, which means the rate goes to 0, right? And that's the case where we have perfectly stabilized particles. So we didn't add any coagulant, or if we did it wrong. We didn't add the right kind, or something. So, or we just tried to let them flocculate when they were all perfectly stable already. Okay, so that's the scale there. We don't really have any equation here to determine. So this is just going to be something that's either given or assumed. So if you see a problem that says particles are completely destabilized, then you know what to assume. Anytime they meet, they're going to stick together, so we'll just put a 1 there. That's probably the most common you'll see. Maybe I might give you a problem that gives you kind of all the other information, and then you have to derive backwards to find, okay, well, under these conditions, what was the collision efficiency here? So it's something we could solve for, given some other knowns. Could be something in practice we could do observationally with this type of a setup. Okay, so that's the collision efficiency, and that's just a unitless fraction. It's just a 0 to 1, maybe it's 0.5, so half the time they meet. That's just going to give us a unitless portion there for the collision efficiency. So then that leaves us with one term that we don't yet understand in terms of what we haven't covered yet. That's the omega term, and this is going to be called Flock volume. It's a volume term in a sense, but it's also unitless, so I'll explain that. So what this is really meaning is if we have some volume of water and there's particles taking up some portion of that volume, so maybe there's a few particles in my water here, well, those particles, given that we say they are spherical and have some diameter, they should occupy some volume in the water, but it's going to be a very small amount, right? Even if this was chock full of particles, very murky water, you could collect them and kind of measure them maybe, but it's going to be some small portion of the total water. So this is actually, when I say flock volume, we are talking about the volume they literally occupy, but we're going to do it on a per volume basis. So it's going to be a volume fraction. So what fraction of this bottle of water is made up of just particles? Okay, so that'll be a pretty small number, and it is then going to be unitless because we did volume per volume. So it's actually volume occupied by particles divided by total volume. So that's why it will become unitless, even though we're calling it flock volume. So this is going to then be a small number. And units have to cancel. So if we're working with something other than cubic meters or something, we have this diameter of particles, maybe that's in micrometers or something, and then we're working with liters of water, we just have to make sure we convert and get our units in line so that they cancel. So it's going to be a small number. It's going to be a fraction, right? It's a very small fraction. Something like 10 to the minus fifth or something, 0.001% of the water bottle, kind of a deal. Okay, so then the way we can describe that flock volume then is essentially the volume of a sphere multiplied by the number concentration. And the reason that works is because, well, the volume of the sphere is one particle, right? So this is essentially saying volume of one particle multiplied by the number of particles per volume. And we see here that if the volume of one particle is pi dp cubed over 6, then n naught is the number of initial particles. So before flocculating, we can just, it doesn't matter if we used n or n naught. Usually we have more information about n naught, right? Usually we start with some number of particles, we know their size, then we're going to send them through flocculation. So normally we're working on the n naught side of things. Technically, we could put in n here if we're assuming we've conserved the volume, which we do assume, and we're assuming they end up as spherical aggregates, which we also do assume for our problems. So it doesn't actually matter that it's n naught, but it's almost always going to be easier to work with it that way. So that gives us, so long as we use that dp here, as long as we were using the aggregate if we used n, right? So we can't mix and match there. So anyway, we're just going to leave it as n naught here. So that'll give us the volume of one particle times the number of particles per volume. Usually, if we convert to meters, this is going to be like meters cubed, and a lot of times this is going to be in liters. So we have to convert the units to make sure they cancel. Just have to track that carefully. Oftentimes that'll be taking that to cubic meters. Does that make sense? Okay. I'm going to, I think I'm going to erase these because I don't want to make any confusions looking back at it later. Okay, so that gives us a fraction of the volume, the total volume that's going to be particles. Then we have everything we need for K. So there's several things that go into this. In a sense, what we have now is it's not just the number of particles in solution that matters in terms of whether or not they're going to find each other. It's actually what portion of the water is actual particles, is occupied by particles. That way, larger particles are more likely to meet each other. It's not just the number that matters. So earlier I was talking about the number of particles matter. Well, yes, but it's also how much volume they're occupying that they could contact each other. So we've got the collision efficiency. That's their likelihood to make a new particle. We've got the flock volume. That's how much space are they occupying. And then we have the mixing intensity. Again, we do assume that we're not mixing too harshly so that we would break apart particles. That's just an assumption. So as we look at it, the higher any of these are, the faster our rate is going to go. There's more aggregation per second. You could look at it, right? So that because it's per second time units. Okay, so let's revisit the problem we did last time with the silt flocculation. So pretty much the same system here, but we're going to say, so we have these 0.01 millimeter silt particles. They are completely destabilized. So as we're reading through the prompt here, we already recognize, okay, there's an assumption being made or given to us. And we did that by adding alum, which is a coagulant. Then we pass it through one of two side-by-side well-mixed flocculation chambers. Okay, so when I read that, I'm thinking, okay, I should draw this up so that I have a mental picture of what's happening here. These chambers are cubic, with each dimension being 3.5 meters. So we were just given the volume of the chambers and the, kind of the size of them. They're mixed with paddle mixers. I'll draw it up with you in a moment. They're mixed with paddle mixers that input 2.5 kilowatts of power into the water in each chamber. And it says the water entering the flocculation chamber contains 10 to the 5th particles per milliliter. And then, so that's giving us a initial number concentration. So then the question is, what is the average diameter of aggregates leaving the chamber? Leaving the chambers. Okay, so at the end of the day, what we're looking for, there's actually a lot of stuff here happening here. So what we're looking for is the average diameter of the aggregates leaving the chambers. So that would be, we can call it dp ag, I guess, or you could just do d ag. Okay, so let's just go ahead and write a couple things down together. So we said complete destabilization. So that means this alpha should be 1. While I'm thinking about it, the K we described just a minute ago, the equation was alpha times 4 times the flock volume times G divided by pi. Needs to be in per seconds. We also had an equation for G, which is the square root of the power divided by dynamic viscosity times the volume of the basin. That power should be in watts. Then we had the flock volume equation, which was and you're given these on the exams. But one thing I would stress is it would be good for you to be thoroughly familiar with what each of the parameters means, right? So that way, like, I would almost say memorize them or commit them to memory, even though you have them, just so you know what the pieces mean, right? You don't have to actually memorize them, but that might be a good way to think about it. Like, oh, okay, this one is, for example, this is the number times the volume of particles, right? So this is going to be the volume equation. This is pi dp cubed over 6 times n naught. Okay. All right. So those are the equations we had. We have complete destabilization. That means our alpha is 1.0. Can never be higher than 1 because you can never have more than one particle formed when particles meet. Then that would be counterintuitive, or less than 1 when they meet, I guess. Okay, so then we have a description of the actual chambers. So we say we had some sort of a coagulation dosing. It's usually a pretty small chamber. So we'll just say that's coagulation added there. Then from here, it's going to 2 side-by-side chambers, each with 3.5 meter dimensions. So these are cubic, 3.5. We have slower mixing happening in here. And then the water will be coming out of these. And going about its way. Okay, so then we know something about the initial particle size, and we are wondering about the size of the particles leaving. Okay, and we still had the same flow rate from that other problem, which is 3 million gallons per day is what's going into here. So the Q going in is 3 mgd. Any questions about this prompt before we begin? I guess there's one other parameter we can write down is we were given the initial, so the N naught, that was 10 to the 5th particles per milliliter. And then we know that we're also given the diameter of the particles, right? So that would be dp. I'm going to go ahead and say that's 10 to the minus 5 meters. Okay, so with that, go ahead and give it a few minutes and see if you can find a way to approach it and essentially set up a mass balance. So since you're being asked for the diameter of the aggregates, you're going to want to do some kind of a mass balance that gets you a relationship between the initial and the final particles. Then you can do we'll do the geometric comparison after that. A few minutes for that. you guys doing with it? Get an answer? Still working? What do you think? Okay. So your answer bigger or larger than the initial particles? Diameter.
It's larger.
Okay, that's good.
So, but I kind of guessed it because I saw it in terms of n notch n. It's like, well, if this is the number of particles in the diameter, go down.
Okay. Okay.
I don't know if this was part of that.
So you calculated the values for those, but haven't put them into place yet, like into something. Okay, that's good. So that's actually a good spot to get to, right? You get your information, you assemble it all, and you see, okay, well, I have values for these different things. That's not a bad way to start. So then, what I'll say is, and how about the rest of you? How far have you gotten? About the same. Got some values, not sure what to do with them, kind of thing. Okay, all right. So that's good. Essentially, it's another problem where you're tasked to solve a mass balance, but in this case, there is the added tricky dimension of, well, how am I going to correlate the final particles to the initial particles in terms of volume to solve for the final particle diameter. Okay, so I will take the first couple steps here and see if you guys see where to go from there. Okay, so we had essentially a flow rate that was split between two. Remember our little drawing. So because they're split and in parallel like this, we're essentially dividing the flow rate in half. So if it was 3 here, then it's just 1.5 here and 1.5 here. So we can then stop and think about just one system, one reactor that has a known flow rate, Q and an N naught, and it's going to have Q flowing out. And this Q, by the way, this is 1.5 mgd, because we're just identifying that one, right? One of the two. And N. We know we have some sort of a reaction in here. That's the flocculation that we're intending. And we should be able to solve for the volume. So now it looks a lot more like a conventional CSTR system that we can work with. So probably the first step would be to isolate just one portion to do a mass balance on. And because these are identical, we only need to do it on one of them, and we can treat it as the same exact thing should be happening in the other, and then we can double the flow and nothing else should change. I mean, when I say double the flow, we can just say that the flows are going to come back together, adding together all the anything that happened to the particles happen in the same manner and all that. So we could go ahead and get the volume of the basin. That's 3.5 meters, and I'm going to cube that entire value. So we know that that's going to be our volume. I can come back to that in a minute. I'm just going to continue setting up, and you probably already solved that part anyway. So regarding this reaction, then what we want to know is some ratio of N naught and N, right? And I said earlier in this lecture that probably N naught over N makes more sense than N over N naught. We've solved these before and said, oh, okay, well, maybe we'll look at N over N naught, get the portion removed or portion remaining, all that. So let's go ahead and say this is a mass balance. We can assume, or we're going to make a mass balance on this. We're going to assume steady state. There's not really a good reason that it shouldn't be. It's been operating this way. It's just, this is what it has. we're not accumulating particles in this reactor in terms of like fewer or more than they were yesterday. So we're going to say 0 then is going to be equal to Q and naught minus Qn plus our reaction term in that volume is going to be a negative VKN. Okay, so far so good. We've got our typical mass balance. Then we're going to solve this for n. I'm going to go ahead and put the terms, both n terms on the other side. So we'll say Qn plus Vkn equals Qn naught. We can go ahead and divide everything by Q. I'm also going to factor out the, well, I'll go ahead and divide everything by Q first. So it'll be n plus theta Kn equals n naught. I'm going to factor out the n's on the left, so we'll have n, so 1 plus theta k equals n naught. And then what I'll do is I'll divide both sides by 1 plus theta k. Actually, you know what? Instead of doing that, I'm going to divide both sides by n. So I'm just going to leave 1 plus theta k over here. That's going to be equal to n naught over n. Of course, we could have divided both sides and then decided to flip it again. Would arrive at the same destination, but here now we have an equation for n naught over n, where this theta would be V over Q. It would be volume of one basin and the Q for one basin. Does that make sense? So if we could label this as 1 and 2. They're identical, so it doesn't matter which one we choose, but what we've drawn and derived is just for one of them. Okay, how does that feel?
Could you do it, when I derived it, I got n equals n naught over 1 plus theta k. Could you still?
Yeah, so a lot of times when we do a first order decay reaction in a CSTR that's at steady state, well, we'll get this form, n over n naught, 1 plus theta k. That's what you said?
Yeah.
Yeah, so you can definitely start there, or if you had committed that to memory, right? That this is a first order decay reaction in a CSTR at steady state. This is the equation you can derive for n. You could certainly then start from there, divide both sides by n naught. That would be n over n naught equals 1 over 1 plus theta k. And you saw my reflex was almost to go there by dividing both sides by 1 plus theta k right here. So then you could do that, and then you could say, okay, well, maybe I want it in terms of n naught over n, and just invert both sides. You get the same thing. Okay. I'll probably want this space. I'm going to erase that. Okay, so do you feel like you know where to go now, or still have some confusion? Okay, so, but this part, getting here was okay once you thought about the system in terms of how it branched, and then just take one of them. That makes sense? Okay, so then from here, what we want to do is make the volume comparison, because we know the volumes, we're still dealing with spherical particles, right? So we should have a consistency in volumes. So, well, let's go ahead and put in the numbers and solve for n naught over n. Some of you said that you have the values here, so I'm just going to go ahead and write it out. It's going to be 1 plus theta k, so V over Q times k. Do you guys have V? Who has V for me? 3.5 cubed.
42.875.
Thank you. Okay. And what about the flow rate? I know it's 1.5 mgd. We had that conversion. Somebody do 1.5 times that for me.
0.0657.
Okay. And then K would have been, and make sure that when you solved for K, well, when solving for K, we had to solve for G first, right? So let's just go ahead and make sure we have a good G. This was square root of the power over mu times volume of the basin. And the power we needed to convert from kilowatts to watts. So that would have been 2,500 watts on top. Somebody have that value for me?
G, I got 225.67, but I got it in 1/2 squared. So I don't know.
Okay, so 1/2 squared. So power is watts, which is joules times seconds, I think.
I used kilograms times meters squared over seconds cubed. That's what Google said.
Okay, read it out again. It's kilograms.
Kilograms times meters cubed all over seconds cubed. I mean meters squared all
Meters
over
squared.
seconds cubed.
Seconds cubed. Okay, so you have seconds cubed in the denominator of the first part. And then the mu s has seconds in the denominator there, which when we divide will come to the top. So that'll leave us with per second squared, right? And then we have square root. So the square so it,
I didn't think
I actually thought about that earlier, but then I was like, there's no way.
Okay, then that's what I got.
I had a different cue.
you got a different Q. Okay, so so what did you do to get your Q?
I just multiplied the 3 mgd times the 0.438
Yeah.
over 1 second mgd, and I got 0.1314.
So that would be so you I think you got the Q for the Q total here before it was split into two branches, I think. So if you divide that by 2, I think you'll get this value. Okay. Great. Yeah, so that's you did it correct for the total. Okay. So then our K was going to be alpha times 4 times the flock volume times G. We now have G. It's all over pi. So flock volume. What did we get for that? And that should be, is it pi times 10 to the minus 5th meters cubed over 6 times the n naught. And the n naught's going to have to be converted from milliliters all the way up to cubic meters, right, as the denominator there. So that was going to be 1,000 for the conversion from milliliters to liters, and then 1,000 more. So it's basically, you're going to multiply that number by 1,000,000 to convert it from particles per milliliter to particles per cubic meter, right? Okay, so if you did that, what did you get for that value?
5.236 times 10 to the negative 10.
Okay. That looks reasonable to me. I'll double check things in a couple minutes with my old file here. But that all sounds correct to me. So with that, then we can, I'm just gonna leave a space here for K. All right, so then putting all those together, what did you get for the K?
I got 0.015.
Um,
Oh, you got
0.015 per second. Okay. Does that look right to everybody? Okay, cool. So then assuming all that's good, then we have 0.015 here. Okay, so we should be able to get a value then for n naught over n. Be 1 plus, and then all this stuff. So while you calculate that, I'm looking back through my old notes that things are, yeah, I'm getting the same numbers from when we did this in the past. And okay, we have a number here. So go, did you get 10.82 or something like that? Thereabout. Okay. Good. So that means we have, on average, 10.8 particles per aggregate. Okay? So that means when we compare our volumes between the volume of the initial particles compared to the final particles, they should be corresponding. Right? So the volumes are going to be conserved. So those should be relatable, right? So then we could say the volume of an aggregate should be 10.82 times the volume of the initial particle. That makes sense? Okay, so then we can say pi d A for aggregate over 6 equals 10.8 2 times pi dp over 6 cubed. Okay, so then we can solve for the diameter of the aggregate by multiplying both sides by 6. Get rid of that. Divide both sides by pi. Get rid of that. And so our diameter of the aggregate should be oops, sorry. Have the cube there. We have to deal with the cubes, but otherwise it's should be relatively straightforward. And when we solve that, I have a number from before giving us 0.0221 millimeters. That would be 2.21 times 10 to the minus 4th meters. Is that 5th? Minus 5th. Sorry. Okay, so it sounds like you guys had the technical parts down for the most part with you. Getting the parameters, getting the units converted, all of that felt okay. And then it was a matter of taking that assumption that the volume is going to be conserved and just deriving what you needed for that, right? Okay, so that was a nice little introduction to what happens when we put two reactors together, right? We had two parallel reactors where we split the flow. And so I'm just going to use this moment to talk about, well, what happens if we do them in sequence? Because that could be a very useful thing sometimes, perhaps. We saw in this case, maybe it's useful to have them in parallel, but what happens if we have it in series? And we'll see this occasionally, and it'll be a good thought experiment to have on hand about like how that's going to work. So let's say we have some flow going through a series of reactors. We have an initial here and one that's the outcome of reactor 1. That's the same stuff that's going into reactor 2. and we have N2 here. We could carry this on with more and more reactors if we wanted to, but this can give us a basic starting point to think about, well, what is that Nx over N naught going to be? It'll depend a little bit on the reactor type as well. If we have a plug flow reactor, that's going to be different than a CSTR. But let's start here with the CSTR that's pictured. And just take 1 minute to think about how you would write Nx, in this case I'll say N2 over N naught. Because that would be if I said how much bacteria is remaining after 2 sequenced disinfection chambers like this, that's what you're looking for, that's the answer. Likewise, you could do a sequenced flocculation chamber, and then maybe we're interested in inverting that, but the process will be the same. So take a moment, I'll just say, let's assume for example, first order decay at steady state. So just like we did a minute ago, we know we have some function that looks like this. Okay, let's use that case example, and you'll see how we could do this to whatever case we have. You've had a minute to think about this and think about how you might approach it. So let me go ahead and give you sort of the shortcut here, or the I guess the way to do it would be to remember that you know something about the N2 over N1. That's in the design. You also know something about N1 over N0 here, or N naught. So you can take them individually, and if you multiply those equations together, you'll see these will cancel. And you can do that with no problem, right? There's no reason you can't do that. So that's going to give you N2 over N naught. Now, that also means that since you have the other side of these equations, right, you can solve this over here for, let's say this is N1 over N0, right? You could just divide both sides by N naught there and get 1 over 1 plus theta K. So you can get your mass balance in terms of N final over N initial for a given reactor, right? Then if you sequence them, then you need to merge those together. And here you can say, well, that's going to be, let's see, 1 over 1 plus, and I'm going to say theta 1, because we'll say there's a theta 1 here. Maybe there's a different reaction basin size, so that could be theta 2. That'd be 1 over 1 plus theta 1 times K. I'll just assume the same K is in there, although you could do K1 and K2. Times 1 over 1 plus theta 2K, and so on. If you have the same size reactors, then you could say if theta 1 equals theta 2, then N2 over N initial is just 1 over 1 plus theta K squared. Okay, so it becomes pretty simple if we have identical reactors. We could think about it in the same way if we had plug flow reactors. Our equation, our overall balance for plug flow reactors is often a little bit different. And in some way, if you think about it, a plug flow reactor is more like a hose So if you sequence one hose and then another hose, it's kind of like you just extended the one hose, right? So plug flow reactors end up being a lot simpler, but assuming you have like the same reaction and stuff, right? So in that case, might be worth thinking about. You might encounter problems like that at some point. But I hope that in addition to some flocculation today, we also took away a little bit about the reactor setups in terms of sequencing and stuff. Okay, so I think that's all I'm going to do for you today, and we'll try to cover most, if not all, of the granular filtration stuff next time. I'll probably invite you over to swing by my lab maybe the time after the granular filtration, because we'll have a demonstration unit of granular filters in my lab. So that's kind of fun. We can play with the flow, the backwash, all of that. Okay, your first homework's due on Thursday, so submit that to Moodle before class starts, and I'll see you then.